Hey guys, I thought today we'd talk a little bit about the history of computing leading into computers themselves so that we can get a better feel for how to use computers for CFD calculations. So I want to lay the foundations for CFD by going over just a bit of the history of computing and then the limitations of computing power available in basic CFD techniques. So oftentimes, if we think about who the first computer programmer is, it's this person here, Augusta Ada King Knoll. And that's kind of cool. She was the Countess of Lovelace, and she was the daughter of Lord Byron. And this is considered the first computer program by some. See, it says diagram of computations by the engine of the numbers of Bernoulli. So this is a program that she wrote in 1842 to calculate the Bernoulli number, which is one of these infinite sorts of convergent schemes. And so she's got it all laid out there. And what's interesting is people have coded this, and this does in fact work. So I guess that's part of what it means to have a computer program. Skipping forward a bit in time, this is Louis Richardson, from which the Richardson number is calculated, turbulent consumption over shear production. You might remember something about that. But Richardson was an interesting guy. He was a pioneer in using computers to solve fluid mechanics problems, and he really worked in the weather prediction area. And he wrote in this paper, Numerical Processes, in 1922, that he's fantasizing about what computers might be like in the future. Imagine a large hall-like theater where the galleries go right around. So he's thinking about a room that has galleries or a balcony that goes right around. And the walls of this chamber are painted to form a map or a globe. And then there's a myriad of computers around this, who are at work around this parts of the map, and each sits in front of a certain section of the map. And when he says computer, he means not what we think of as computers today, but an actual person who is a computer, like calculating numbers and things. So each one of these persons attends to only one equation or part of an equation. So he's imagining that you're going to do the calculations for whatever, some section of the map. The work of each region is coordinated by an official of higher rank. The numerous little night signs display the instantaneous values so that neighboring computers, neighboring people can read them. So when you calculate your value, you would display it, and then the person next to you could read it. So if I were doing a central difference scheme, I could read the two numbers next to me and then do my calculation. That's pretty awesome, right? Each number is thus displayed in three adjacent zones to maintain communication of the north and the south of the map. So the galleries are also formed so that people can see it up and down. From the floor of the pit, a taller pillar rises to half the height of the hall. In this sits a man in charge of the whole theater, and he is surrounded by several assistants and messengers. One of his duties is to maintain the uniform speed of the process so that somebody doesn't get ahead, right? Everybody's kind of together at an instant in time, then they calculate the next instant in time, continuously advancing the solution around this whole gallery. Pretty crazy, right? So is that it in respect to, right, he's like a conductor of an orchestra. 4 senior clerks from the central pulpit are collecting the future weather as fast as it's being computed and dispatching it via the quiet room where it's telephoned or radio transmitted or whatnot. So the keys are, there's a myriad of computers. You know, he's talking about parallel computing. They're at work together. They're working on a map, a discretization, and he's got 3 adjacent zones. So he's really, that's a pretty high order stencil there that he's thinking about. And these are the computers of the day. These were actually people that did these computations in computer rooms. I love this sign right here, computing division, computing section. See, these are folks just working on mechanical adding machines, adding, subtracting, multiplication, and division. That's all you need. And if you wanted to set up a computation, you would just organize these people into a grid, and they would pass the numbers to and fro as if they were central difference nodes or boundary condition nodes. This guy here at Harvard, Pickering, he set up computer. So he organized these workers here that he's got into groups, and they would literally do what I just described. They would pass the numbers back and forth and fore and aft in order to do computations. I thought I'd throw a Jesuit in here, right? Roberto Busta. It was a Jesuit. He used computers for linguistic computations to look for words and repeating words and things. Let's talk about the first, what we think of as a computer. So we went from people, called the computers, to an actual machine that would do the computing for us. And this Interac is a very famous computer. It basically came online in 1946, and it stood for Electronic Numerical Integrator and Computer. And there's a couple of folks there working on it. And it was the first Turing-complete computer, meaning that you could program it. So you didn't have to go and rewire it for a program. It was actually programmable, electronic, general-purpose a programmable computer. So that was a Turing complete. And maybe a coffee break is, if you don't know who Alan Turing is, go watch The Imitation Game. It's quite good. It cost $500,000 to build. Seems like a lot of money. It was primarily used for calculating artillery firing tables, so like given an angle and maybe how much powder was in there, how far would the projectile go. It was also used to study the feasibility of thermonuclear weapons, so doing hydrocodes type simulations. It had a speed on the order of 1,000 times faster than that of the electromechanical machines of the day. It was huge. 17,000 vacuum tubes, a whole bunch of crystal diodes and relays and resistors and capacitors and so forth, all hand soldered, 5 million hand soldered joints. It weighed 30 tons, took up a room that was, 10 meters by 16, almost 17 meters. That is huge. You're just looking at just a section of it here, right? It went on and on. It used 15 kilowatts of electricity. Here are some of the programmers of the early computers. They were called subprofessionals because they were basically folks coming out of the computer pool, right? These computers then naturally migrated into programming these computers. So a lot of those early programmers were actually folks coming right out of the secretarial pools or the computer pools. And they're quite famous. A lot of these folks, there's like the pioneering, IEEE Pioneering Award is named after Betty Halberstam. Anyway, I think these are cool looking pictures of what computers looked like in the day. Here's a famous computer programmer, one of the early computer programmers. This is a picture taken of her later in her life. You can see she spanned the sweet spot of those early computers. In her career, she made it to Rear Admiral in the Navy. That's quite a high rank. She was the first computer programmer of the Harvard Mark I, 1944. She invented the first compiler for a computer programming language. She helped popularize the idea of machine-independent programming languages. So you could write a computer programming language like COBOL, which she was instrumental in formulating, and bring it to a different computer. It would still run. So there needed to be some sort of formalization of that. These are what the computers look like. So this is the Mark II. This computer is near to my heart because it was installed at NSWC Dahlgren. So this is where I worked for 5 years before coming to Marquette Naval Surface Warfare Center in Virginia. There she is there at the station of an Interac. But she wrote this, she was trying to diagnose a problem with one of her computer codes, and so she got into the panels and she found that, look what it says here, in relay 70 in panel F, there's a moth in the relay. First actual case of a bug being found. So literally, the term bug, she coined it, and it was when this bug, this moth, got in a relay. So there was a bug in the computer, and you had to go get them out of the relays so that they would operate correctly. And this piece of paper is now in the Smithsonian out of her logbook, the first bug. I like that. Anyway, here's modern computers. Here's the rank for 2016. Here's the fastest computers in the world by the number of flops they can do. So that's a floating point operation per second. That's a teraflop floating point operation. There's the fastest, there's the second fastest, third. See, it drops off pretty quickly. So the fastest right now is in China. The second fastest, or the fastest in the U.S., is at Oak Ridge National Laboratories, DOE computer. That one's at Lawrence Livermore National Labs, part of with the NSA and so forth. So you can see them going on down the list. This is what the fastest computer in the world looks like. That's in China. Notice all of these run Linux, right? They're not running Microsoft or Macintosh type operating systems, although Mac is really a Linux-based system. So here's Titan. This is currently the fastest in the U.S., right? It is pretty big, as you can see. Like if a person was standing right there, they'd be about that tall. It is a total of 300,000 processor cores. That's amazing, right? And this is the amount of GPU RAM on there. So that is amazing. There's a picture of it from the top. It's composed of 18,000 AMD Operons, 6,200 16-core CPUs. That's a lot. It costs $97 million to build, and it takes 8.2 megawatts of power. For example, my little Mac Pro here in my office takes 0.5 kilowatts of power, so that's 4 orders of magnitude different. The Interac took 150 kilowatts, so that's kind of interesting. But I found this most interesting. The Valley Power Plant here in Milwaukee produces 136 megawatts. So at 8 megawatts, it takes a pretty good chunk of the Valley Power Plant, what powers the city here, just to run this Titan computer. It held the #1 spot for about a year or so back in 2012, 2013, and it was overtaken by the Chinese computer here. I'm not sure how to say that, Tianhe, but it's expected that Sandia is currently building a computer they call Summit that will overtake it. DOE is currently building this computer that they expect to overtake it. So these things change all the time, right? Here's Garnet. This is a computer, a quote, supercomputer that I have access to, and it's 8 nodes, log-in nodes, and where's the good stuff? It is built on AMD's, oh yeah, the compute nodes. There's 4,700 compute nodes, and each compute node is an AMD. So that's a lot of computers all tied together that can communicate. Let's talk about how to characterize computers. We talked. I pointed out the number of flops. Flops is characterized this way. Take the number of sockets on the motherboard, and then the number of cores per socket on the chip, and then you take the chip speed, and you multiply that times the number of floating point operations per cycle, right? Together, that'll give you the floating point operations per second, the total number that the computer can do. So my Mac Pro in my office has 8 cores. It has 2 floating point units. It is 3.2 gigahertz, that's the clock speed. It'll do 2 flops per cycle. So in total, it'll do 102 gigaflops per second. So that's 102 giga floating point operations, like 2 plus 2 is a floating point operation per second. That's impressive. But look at how fast these guys are, right? Here's Titan, and here's this Tianhe 2. They just smoke this thing, right? A tera is 3 orders of magnitude bigger than a giga, and then it's one more, so it's 10,000 times faster than my MacBook Pro. Of course, the first computer I ever owned back in 1983 was a Commodore 64. It would do 0.5 megaflops. So kind of the difference in these two, an order of 4 orders of magnitude, is the same from my first computer to now. So that's kind of interesting to think about. If you've never heard of a Commodore 64, it was crazy popular when I was in high school. It cost $600, and it still holds the Guinness World Records as the highest selling computer of all times. They sold 10 to 17 million units, so it was a crazy popular computer. Here's Moore's Law. I'm sure you've seen Moore's Law before. It's basically showing you over time, over the years, how fast computers have gotten. And you can see this is a log scale, right? 100 megaflops, a gigaflop, 10 gigaflops, 100 gigaflops, a teraflop. Here are the fastest computers in red. So you can see, the Fujitsu got overtaken by the Intel Red, which got overtaken by white, and so forth. There's Blue Gene, that was a famous one that made a lot of press. But, this is kind of a straight line and log, so it's exponentially increasing. Just to give you an idea, like the 500th fastest computer back in whatever this is, 2011, is, what is that? About 2 orders of magnitude less than the fastest. And then here's our notebook, which is 1, 2, 3, 4, 5 orders of magnitude than the fastest computer in the world. So that's kind of interesting. And we expect this to continue to rise possibly. That's Moore's Law. So this is showing another version of Moore's Law. Instead of like the flops, this is calculations per dollar. What does it cost to build these things? And these are chipsets upon which we're looking at. So not necessarily a computer, but just the chipset itself is moving from electromechanical to solid state to vacuum tubes, transistors, and now integrated circuits. And really, if we want to just keep pushing this up on this curve that they're showing here, which is even steeper than exponential, at some point we need to cross over this optical quantum DNA computing. So we're going to have to really set a whole new paradigm for the way that these things work, leaving the integrated circuit regime that we've been in for the last 20 plus years and entering into this quantum computing regime. So this is showing the same sort of plot. Number of transistors that you can pack into a small space directly translates into how fast this computer is. Over this range, the number of transistors has increased exponentially, right? Showing that it doubles every 2 years. This is the same sort of plot. This is million point operations per second, or million iterations per second. So we're up to the billions here. Showing again, these are individual computers and where they fall on this trend, and showing you kind of the equivalent of how many floating point operations are in these different regimes, like bacteria, worms, and here's humans up here. So it looks like back in this plot had the same sort of thing, the mouse brain and the human. So to get to this next level, we're really going to need to jump to the quantum computing. Here's Moore himself, this guy is still alive. Born in 1929, he's the co-founder of Intel Corporation. He has a PhD in chemistry and physics. I didn't know this, but he's worth $6.2 billion. He's 201 on the Forbes richest list in 2016. That's amazing. In 2005, Moore stated in an interview that it just can't go on forever, right? Transistors eventually will reach their limit of miniaturization at the atomic level. So people believe there is a strict end to Moore's Law. Some people think it's going to be around 2015. That's that quantum computing barrier that I mentioned. But some people think that it just will go on for at least another 250 or 600 years. I guess we'll just have to wait and see. Moore viewed his law really as an optimistic view in total contrast to Murphy's Law, right? Which I think is kind of funny. Murphy's Law, everything is going south, but in Moore's Law saying everything just keeps getting better and better. So there's these quotes here by some people. I thought it's always fun to look at these old quotes. I think there's a world market for maybe 5 computers. That was Thomas Watson, president of IBM. IBM, remember, was International Business Machines. They made mostly typewriters and calculators and things. They got into the computer business. But people misquote this guy as thinking he was short-sighted. He meant there's a world market that year for maybe 5 computers. They might sell 5 computers. These are the real short-sighted guys here. It's very possible that one machine would suffice to solve all the problems that are demanded of it from the whole country. This guy's British. He's the great-grandson or the grandson of Charles Darwin. He was the head of NPL, which is National Physical Laboratory, kind of the equivalent of Los Alamos. He thought one computer could solve all the problems of the country. That's pretty short-sighted. Originally, one thought that there were a half-dozen large computers in this country hidden away in research laboratories. That would pretty much take care of all the requirements we had in the country. Thank you, Howard Aiken, conceptual designer at Harvard's Mark I computer. So people just can't predict the future, even if they're pretty bright folks. Anyway, that'll do it for this talk. I'll see you again next time.